Okay, so let's look at one of the most basic levels of security, and that's layer 2 security, looking at VLANs or virtual LANs. So what is a virtual LAN? A virtual LAN involves creating a logical network. In this case, all these nodes connect to the same switch, but we can segment them so that certain ports connect to one VLAN and other ports connect to another VLAN. The two networks cannot communicate directly through the switch. So in this case we have PC 9, 16 and a server connected to one VLAN. This defines the scope of the broadcast domain, and then PC 1, 8 and server 1 connect to another VLAN. So in this case we can apply security at the very lowest level. So why do we use VLANs? Well, VLANs allows us to create networks across multiple switches. We can see here that these machines need to be connected together in one LAN, but this machine connects to a different switch. Through trunking, it is possible for us to span VLANs across switches. So now, even though these three machines connect to the same switch, they are not connected to the same network. Again, VLAN 2, we can span across the various switches. What we need is a trunking backbone. And basically what will happen when a broadcast happens from one node, it will be sent to all other nodes in the VLAN and not to another VLAN. So it will be sent across the trunking route to the other switch. Same again, a broadcast here will be sent to this node through the trunk and then also to that node. So an example of VLANs is implemented in a switch or in a Cisco Aeronet. So the advantage of VLANs is that we can set up microsegmentation, where we can split the bandwidth up into smaller and smaller elements. We have enhanced security, where we can isolate one part of the network from another, even though machines connect to the same switch. We can relocate servers away from local machines and put them into places like server farms, but the hosts still stay connected as if they were connecting to a local LAN. And it allows us to create subnets very easily. Along with this, we can create virtual networks, and it should help to ease administration in that we can move resources wherever we require them. Along with this, it improves the bandwidth usage as network traffic stays within a certain workgroup. If we have a great deal of local traffic, such as to servers or disk farms, we can keep it local inside the same VLAN, and it doesn't affect other VLANs. Okay, so let's see how we configure our VLANs. Basically, there are two types: a static VLAN, where nodes are permanently assigned to a VLAN, typically depending on the port that they actually connect to. We can also have dynamic VLANs, where a user or a certain machine, no matter which port on the switch they connect to, they will still connect to the same VLAN. For this, we need a database which defines the VLAN that users or nodes connect to. Typically, it detects a MAC address to assign the VLAN. Static LANs are extremely secure, and they need to make sure that a certain machine connects to a certain port. So for static VLAN, what we have here are two nodes that connect to the same VLAN, and we have two other nodes which connect to the second VLAN. These ones connect to VLAN 1 and these ones to VLAN 2. So what we do is that we create our VLAN. VLAN 1 is normally created anyway, but we create it with interface VLAN 1 and we enable it with no shutdown. We create VLAN 2 and again we enable it. Now we can assign each of the ports to the VLAN. So switch port access VLAN 1 will assign this port to VLAN 1. For the third port, we assign that to VLAN 1. So now these two machines are in the same VLAN and can communicate directly. These two machines are then, these two interfaces are then connected to VLAN 2. So these two can now communicate. If we try to ping from this machine to that machine, we can see that it is successful. But if we try to ping from this machine to this machine, then it is unsuccessful, as we can see here. The only way that these two devices can actually communicate is through a layer 3 device. The basic VLAN types that we have is that we can allocate it by port on the switch. We can define MAC-based VLAN. Depending on the MAC address, it will assign it to a certain VLAN. We can define it for protocol such as IP or IPX. In a wireless system which has multiple SSIDs, we can assign each SSID to a certain VLAN. That allows us to span across various aeronets and still connect to the same VLAN. And we can also have ATM VLANs for switching ATM cells. In a dynamic VLAN system, we need an MPLS server, typically run on a 6000 series switch. And this device actually contains the database which maps the MAC addresses to the VLAN numbers. So in this case, we define our VLAN and we give it an address. The reason we give it an address is it's so that we can access it remotely to be able to configure it. Then we say that the VLAN allocation is dynamic for the two ports that we have here, 1 and 2. And then we define the VMPS server. In this case is the .2 machine, which is the switch. As this is so important, if there was a failure on the switch, then we typically define a secondary VMPS server. So in this case, this is the primary and the system will try this switch first. If we define a secondary, then it would go to the other machine. We can have a reconfirm and a number of retries. If it doesn't manage to contact it, it will try again for up to 3 times. The reconfirm will go back every 60 minutes in this case and reconfirm the allocation of the VLAN just in case that it's been allocated to another VLAN. So these commands define the VMPS server for reconfig and retry, and then when we say show VMPS, it shows us the basic details of the VMPS server. On the VMPS server, we typically have our configuration on a TFTP server, and when the machine is booted, it loads up the VMPS file, defines the domain, and then defines the mapping of, in this case, the VLAN name staff is allocated to this IP address, this MAC address, and students is allocated to this MAC address. So in this way we can allocate our VLANs in terms of a VLAN name. So with inter-VLAN, we need to be able to send our VLAN information across a trunking route so that we can join up our nodes across multiple switches. So we typically reserve one port on each switch purely for a trunking route. We can also do layer 3 with a layer 2, layer 3 switch, so that this machine can actually talk to this machine, but only through a layer 3 interface. And at layer 3 we typically define firewall rules to either block or allow traffic at layer 3. We can see here an example of between a switch and an aeronet, where we can have various SSIDs. In this case, this machine connects to VLAN 1 SSID, this is VLAN 2. Then through the switch we can map up machines that are connecting to a fixed network and become part of the same VLAN. Okay, so let's look at some more VLANs. The trunking protocol that's used is 802.1q. 802.1q is enabled to allow the trunking to happen, and basically it adds extra information onto the data frame which tags the VLAN that the node is in. So we have a normal data frame, it goes through the switch, 1q adds this extra information to define the VLAN, goes across the trunking route, the switch picks it up, strips off the VLAN information, and then is sent to the required node within that VLAN. So basically the way that it's done is that in the Ethernet frame we have some preamble, a destination MAC address, source MAC address, and then we have Ethernet type. At the end we have a basic check sequence. Then in between we have some data in here, which can be up to about 1500 bytes long. About 1516 bytes is around the maximum length of a data frame. So when we carry ARP traffic, we should see the value of the hexadecimal value of 0806. If it's an IP packet, 0800. If it's a 1Q tagged, we should see the ether type of 1800. So we can see here an example. This is an IP data packet with inside our Ethernet frame. So here we see the destination MAC address, here we see the source MAC address, and then we get an ether type of 0800, which is an IP packet. So the way the encapsulation is done is that if we have our ether type of 1Q, then the bit that comes after it is then added. We can have 8 levels of user priority, a CFI bit, and then we can have a 12-bit VLAN number. 12 bits allows us to create between 0 and 4095 VLANs. So the maximum number of VLANs that we can have on a site is 4096, which should be enough for any network. The Ethernet type is then just added at the end of this, so that when the data frame is recovered at the other side, the red parts are taken off and it recovers the original Ethernet frame that originated on the original network. So this is defined as an encapsulated data frame. So we can see here another method is an ISL trunk, and this is less used these days because this is a Cisco derived protocol and it doesn't embed into the Ethernet frame as 1Q does, but it adds an extra header. For compatibility reasons, this is also supported on many switches. We can see here when we define our trunk, we say encapsulation and we can make it 1Q, ISL, or it can negotiate between the switches on the best type of encapsulation used. So how do we trunk between our VLANs? So in this case we have 2 nodes connected to one switch, 2 nodes to another switch, and we're using the third port on each switch as a trunk. So we set up a connection between the two on those ports. So we can see here that we define that are two VLANs, and we can assign them with different IP addresses to be able to communicate with them. Port 1 and port 2 on this switch are used as layer 2 access, and then then the third port is encapsulated with one queue. It then defines the native VLAN, which means that the data frames are not tagged, and then it defines the VLANs that are allowed to be trunked. And in this case it's non-negotiable. So now we have a trunking route between the two VLANs. If we wanted to assign this one to VLAN 1, then we would use the VLAN assignment here for VLAN 1 and then here for VLAN 2. So this shows an example of VLANs. We would set up on this AeroNet trunking route to the switch, trunk here and a trunk here, and then all these nodes can connect to the same VLAN. So on a wireless access point, we can define the SSID that we're going to allocate. In this case we have an SSID of Scotland. We assign that to VLAN 1, and for England we assign it to VLAN 2. And then what we do is that we define a sub-interface for these VLANs, which provides two virtual interfaces, and we say for the radio port .1 the encapsulation is 1Q, and the same again for the other radio interface. We have a .2 sub-interface, and that's allocated to the second VLAN. So nodes which connect to this SSID will be allocated to VLAN 1, and for this SSID will be allocated to VLAN 2. Then when we look at our VLAN information within inside the AeroNet, we can see that we have two virtual interfaces for our connections using 1Q encapsulation. On the switch, in this case we set up our two VLANs and we create them here. There's no need to allocate an IP address if we don't need to access it remotely. And then in this case the first port is allocated as a trunking port, the second one for trunking, and the third one for trunking. So it trunks in between the AeroNets. Okay, so this is a similar example, VLAN 1 and VLAN 2, and this shows our encapsulation. An important protocol that is used in switching is VTP, and VTP is important as it radiates information about VLANs across trunk routes, so that it is possible to discover the whole of a network and find out where VLANs are across these trunks. So VTP also allows us to be able to add and delete and change VLANs within inside a domain. So to create this, we create our VLAN database, define the name of the domain, and whether our device is a server or not. Various applications of VLANs. As we've seen, we can connect wireless access points into the same VLAN as we have here. Then we can have layer 2, layer 3 switching in between, so that we can actually interconnect devices through the layer 3 switch, or we can block communications at layer 3. And that's the end of this presentation.